Section 11.4 is the comparison tests. So when you do a comparison test, the idea is that you compare a given series with a series that you know is either convergent or divergent. So think about the sum from n equals 1 to infinity of 1 over to 2 to the n plus 1. This makes us think about the series, the sum equals 1, the sum from 1 to infinity of 1 over 2 to the n. Now when we look at this series, this is 1/2, 1/4, 1/8. This one's geometric because we have multiple powers of n. So it's a geometric with a equals 1/2 and r equals 1/2. Since that's the case, it's convergent. Since the absolute value of r is less than 1, this series is convergent. So that should help us with the other series. So the series that we were given, the series up here in blue, it's very similar to our convergent series. So we think it's convergent, but if you think about this, 1 over 2 to the n plus 1 is less than 1/2. The terms of this would be 1 over 3 plus 2 squared is 4 plus 1 is 5. 8 plus 1 is 9. 16 plus 1 is 17. So you can see that each of the terms is smaller than the one before. So the partial sums are also smaller than 1, and it's a bounded increasing sequence, so it's convergent. So the sum of this is less than 1. Similar reasoning can be used to prove the comparison test, but here's your comparison test. It says the comparison test. Suppose that the sums an and bn are series with positive terms. So part 1 says if the sum of bn is convergent, and an is less than or equal to bn for all n, for all values of n, then the sum of an is also convergent. So if we know our series is convergent and our unknown series is smaller than our known series, then the smaller series is also convergent. We're going to look at a similar result for the divergence. So if the sum of bn is divergent, now here's where it gets big, where it makes a difference, because in this case, an is greater than or equal to bn. So it has to be larger for all n. Then the sum an is also divergent. So let's look at a problem. It says determine if the series from n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 is convergent or divergent. So while we do this, let's look at this fraction, and let's compare it with the largest term in the numerator. In this case, there's only 1, and then the denominator is 2n squared. So the first fraction is less than the second fraction. So let's consider the series for the second fraction. So we have n equals 1 to infinity over 5 over 2n squared. So this 5 is a constant, so is the 2 for that matter. So we could say the sum from n equals 1 to infinity of 5/2 times 1 over n squared. So the constant can come out of the summation, n equals 1 to infinity of 1 over n squared. Now that's a p-series. This is a p-series with p equal to 2. So go back and look at your notes. Since 2 is greater than 1, then we have convergent for this one. And since our original equation is convergent, is smaller than this one, too many words, let's try that again. We know that this series is convergent. And since our given series is smaller than our convergent series, we can say, therefore, the sum from n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 is convergent by the comparison test. So we have a convergent series here in blue. We have a series smaller than our convergent series. Therefore, our given series is convergent. Let's look at another one. It says the sum from n equals 1 to infinity, and we have ln of n over n. Now, we did this one in the last section. Probably the integral test here works. You can do the integral from 1 to infinity and look at the improper integral. But here what we want to do is we want to consider the comparison test. So when we think about the comparison test, this compares easily with ln of n, and let's compare it to 1 over n. Now 1 over n is the harmonic series that we looked at back in section 11.2, I believe. But if you think about 1 over n, it was divergent. We know that the first fraction is greater than the second fraction because the denominators match, and natural log of n is greater than 1 over n. And that's true when n is greater than or equal to 3. When n is 1, you actually have 0 over 1, which is smaller. So we're looking at it for n is greater than or equal to 3. So for n equals 1 to infinity, 1 over n is divergent because it's the harmonic series, and we proved it a couple lessons ago. It's a good one to know for your comparison. And so here we have a divergent series, and then we have a given series where the fraction is greater than the other one, than the comparison. So we can say that the sum from n equals 1 to infinity of natural log of n over n is divergent by the comparison test. So the important thing to remember is that if you have a divergent series, the other series has to be larger than that. Let's run back to the comparison test real quick. If we start with a convergent, we need a smaller series. If we start with a divergent, if we're comparing a divergent, then we need a larger series. So consider this problem. It says the sum from n equals 1 to infinity of 1 over 2 to the n minus 1. Now this is similar to what we looked at earlier. Let's take 2 to the n minus 1 and compare it to 2 to the n. 2 to the n is 1/2, 1/4, 1/8. And 2 to the n minus 1 is 1 plus 2 squared is 4, take away 1 is 3, 2 to the third is 8, take away 1 is 7. Now when you compare these, this fraction is larger than the other fraction. But we have that the sum from n equals 1 to infinity of 1 over 2n is convergent because it's a p-series. Remember, we just looked at this one a minute ago. P equals 2, which is greater than 1, so we have convergent. So here's our problem. Here we have convergent and greater than. So the comparison test does not help us here. And since we're looking at the comparison test, we're going to let this one go for now. The comparison test is not helpful. well, let's not let it go. Let's look at the next one. The next the next test is called the limit comparison test. It says, suppose that the sum of AN and the sum of BN are series with positive terms. So then we know that if the limit as m approaches infinity, n. If the limit as n approaches infinity of an over bn equals c, where c is a finite number, that means it's a definite finite number, and c is greater than 0, then either both series converge or both series diverge. So let's go back and look at that series we were looking at before. So if we can look at the limit, here's your key. If you can look at the limit of an over bn, then if c is a finite number and positive, then either both series converge or both series diverge. So let's go back to what we were looking at. Let n equal 1, the sum from n equals 1 to infinity of 1 over 2 to the n minus 1. So what we were considering before was we had this series, and we have b of n, which is 1 over 2n, where the series of 1 over 2n converges. Now that's important. It doesn't do you any good to look at two series where you don't know anything about either one. So let's look at the limit as n approaches infinity of an over bn. So this is the limit as n approaches infinity. Been playing in improper integrals. The limit as n approaches infinity of an, which is 1 over 2 to the n minus 1, 1 over 2 to the n. Now remember that long fraction there, it means to divide. So we're going to take 1 over 2 to the n minus 1, and we're going to divide it by 1 over 2 to the n. That means we're going to flip and multiply. So we say the limit as n approaches infinity, 1 over 2 to the n minus 1 times 2 to the n over 1, which is the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. Now, when you get here, you plug in infinity, and you have infinity over infinity, which is an indeterminate form. So you can use L'Hopital's rule. I like L'Hopital's rule. You can divide by 2 to the n power everywhere. Let's use L'Hopital's rule. So we have the limit as n approaches infinity. Remember, L'Hopital's rule is the derivative of the top and the bottom separately. So the derivative of the top, the derivative of 2 to the n is 2 to the n ln of 2. And the derivative of the bottom is 2 to the n ln of 2. And those cancel because they match. So we have the limit as n approaches infinity of 1, because these cancel as well. So that limit is 1. By the way, this would be c. It's positive. It's greater than 0. Therefore, by the limit comparison test, we can say that the sum from n equals 1 to infinity of 1 over 2 to n minus 1 converges because the comparison series converges. Okay, the next problem says to consider the series from n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the fifth. So when you look at this, we're going to compare these fractions. The square root of 5 plus n to the fifth. This is my first one. This is an. And bn is the leading term here is 2n squared, and the leading term in the denominator is the square root of n to the fifth. So let's rewrite this as 2n squared over n to the 5 halves. Now this can be simplified even further because I have 2 n to the 4 halves on top and n to the 5 halves on bottom. So this is 2 n to the 1 half. By the way, the sum of 2 over n to the 1 half can be written as 2 times the sum of 1 over n to the 1 half, which is p series, and 1 half is less than 1, so this one is divergent. So keep all that in mind. That's important. So let's use this one to look at the limit comparison test again. So we're going to say the limit is n approaches infinity of an over bn. So this is the limit as n approaches infinity, and an is 2n squared plus 3n over the square root of 5 plus n squared to the fifth. That just looks bad because it's small. And then on the bottom, the series on the bottom is 2 over n to the 1 half. So again, we have a fraction divided by a fraction. So we have 2n squared plus 3n over the square root of 5 plus n to the fifth times n to the 1 half over 2. This gets nothing but messy. So let's distribute on the top and pull this 2 to the front. So we have 2n to the squared plus n squared times n to the 1 half is n to the 5 halves, plus 3 n to the 3 halves over 2 times the square root of 5 plus n to the fifth. I think L'Hopital's rule is messier than dividing by your highest power of n in the denominator. So let's divide by n to the 5 halves because that's what we have in the denominator. So we have 2n to the 5 halves. I'm going to need more space. Let me try this again. So we have the limit as n approaches infinity. And we have 2n to the 5 halves over n to the 5 halves plus 3n to the 3 halves over n to the 5 halves. And then we have this over n to the 5 halves. So we have the limit as n approaches infinity. Sorry about that. We have 2n to the 5 halves over n to the 5 halves plus 3n to the 3 halves over n to the 5 halves. And we have 2 times the square root of 5 over n to the fifth plus n to the fifth over n to the fifth. Because we have a note here that the square root of n to the fifth equals n to the 5 halves. So it allows us to move it in. Now you can see these cancel. So we have the limit as n approaches infinity, we have 2 plus 3 over n. And on the bottom, we have 2 times the square root of 5 over n to the 5th plus 1. Now, when you plug in infinity, 3 over infinity goes to 0, and 5 over n to the 5th goes to the 0. So we have 2 over 2 square root of 1, which is 1. And 1 is greater than 0, it's positive. So we can say, therefore, we know that Bn is divergent from here. So since our limit goes to a number that is positive, then we can say that our given series back here is also divergent. So we're going to say, therefore, the sum from n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th is divergent by the limit comparison test. They make a note, the big note to make here is that when you're looking at your limit comparison test or just your comparison test, you're going to consider your terms with the highest degree in both the numerator and the denominator. So I think that settles it for 5.4, I'm sorry, section 11.4. Let's do one more of these. I'm thinking we might have time to do 2. Let's do the sum from 1 to infinity. This one says e to the n plus 1 over n e to the n plus 1. So if we let this equal an, and let's let bn be e to the n over n e to the n. That's our leading terms. So these cancel, and we have 1 over n. Remember that the sum of 1 over n is the series of 1 over n is the harmonic series, and it's divergent. So then we can say the limit as n approaches infinity of e to the n plus 1 over n e to the n plus 1 divided by 1 over n, because we have an over bn, sorry. So we have the limit as n approaches infinity, e to the n plus 1, n e to the n plus 1 times n over 1 gives us the limit as n approaches infinity of n e to the n plus n over n e to the n plus 1. So let's use L'Hopital's rule here. When you plug in infinity, we have infinity over infinity, which is indeterminate form. So we have the limit as n approaches infinity. The derivative of n e to the n is product rule, so keep the n. The derivative of e to the n is e to the n, plus the derivative of n is 1, and you keep the e to the n. So that's our product rule. And then the derivative of n is 1. And on the bottom, we have the same product rule, n e to the n plus e to the n, technically plus 0. So when we plug in infinity, we still have infinity over infinity, not helpful. So let's do L'Hopital's rule yet again. So we have n, keep the n, the derivative of e to the n is e to the n. The derivative of n is 1, and then we have e to the n plus e to the n. And the derivative of 1 is 0. So on the bottom we have, you keep the n, and the derivative of e to the n is e to the n, plus the derivative of n is 1, and then we have plus e to the n. By the way, those two terms match exactly, so we have the limit as n approaches infinity of 1 is 1, which is greater than 0. So remember up here that our comparison series was divergent. Therefore, we can say, therefore, the series from n equals 1 to infinity of e to the n plus 1 over n e to the n plus 1 is divergent by the limit comparison test.